Hello and welcome to Brunei Math Club. In this video, we study elementary column operations as opposed to elementary row operations. That is, instead of swapping two rows, we swap two columns. And instead of multiplying a one row by a constant, we multiply a column by a constant. And instead of adding a multiple of one row to another row, we add a multiple of one column to another column. By combining elementary row operations and elementary column operations, we show that any matrix can be transformed into this form. That is, we have ones in the upper left corner of the matrix and everything else is zero. Okay, let's start. First, let us review the relationship between the elementary matrices and elementary row operations. So Pij, Pi of C, and Pij of A are elementary matrices. First, if we multiply Pij to a matrix A from the left, we have this. That is, the two rows, the ith row and the jth row, are swapped. And if we apply Pi of C to A from the left, Pi of C is this. So all the diagonals are 1 except for the ith diagonal element, which is C. Then if we calculate this, we get this matrix. That is, the ith row of the matrix A is scaled by C. And lastly, if we apply Pij of A to A from the left, Pij of A is this matrix. That is, it's identical to the identity matrix except for the ij element, which is A rather than 0. Then this results in this matrix. That is, A times the jth row is added to the ith row. So, multiplying an elementary matrix to another matrix from the left, that results in an elementary row operation. Now, what happens if we multiply an elementary matrix to another matrix from the right rather than from the left? Let A be an m by n matrix, and Pij, Pi of C, and Pij of A be elementary matrices of order n rather than of order m. First, consider this product. So we multiply Pij to A from the right rather than from the left. This corresponds to swapping the ith and the jth columns of matrix A. So let's see this. So we have this, and this is matrix A, and this is the matrix Pij. This is the ith column, and this is the jth column. And this is ji element, and this is ij element of matrix Pij. So first consider this row and the ith column of this matrix. So if we do this multiplication, we get A1j. And consider the first row and the jth column. So we do multiply this and this, we get this, A1i. So if you continue this for every row and every other columns in these matrices, then we obtain this matrix in which the ith row and the jth row are swapped, and all other columns are unchanged. And next, consider this product, A times Pi of C. This corresponds to multiplying the ith column of matrix A by the constant C. Let's see this. So we calculate this product, and this is the ith column of matrix A, and this is the ith diagonal element of this elementary matrix. So if we do this multiplication, we obtain this matrix in which the ith column of matrix A is scaled by the constant C. And finally, consider this product, A times Pji of A. Be careful, it's not Pij of A, but it's Pji of A. Be careful with this order of indices. And this product corresponds to adding the jth column of matrix A multiplied by A, this constant, to the ith column, which we denote by this. So let's see this. So A times Pji of A is this. This is the ith column, the jth column, and this is Ji element rather than Ij element. So if we multiply this row with this ith column, then A1i times 1, A1j times A, we get this. Everything else in this column is 0. And considering this times this column, this is the jth column, so everything else except for this one is 0, so we only get A1j, which is this. So if you continue this for all other rows, all other columns, we get this matrix. So the ith column has been changed. It's been incremented by A times the jth column, original jth column, and everything else is unchanged. So these three operations are elementary column operations. Now let's see one example. Consider this matrix. By applying a series of elementary row operations, we can obtain this reduced echelon form. So applying elementary row operations means multiplying elementary matrices from the left. So a series of finitely many elementary row matrices from the left, this matrix can be transformed into this matrix. And in reduced echelon form, we have this staircase pattern. And at each step, only one element is 1 and everything else is 0. And if the step doesn't change, then we may have many non-zero elements in the column. So starting from this reduced echelon form, let's apply some elementary matrices from the right. Okay, first let's try this one. So if we apply P14 of -2, that means we multiply the first column by -2 and add that to the fourth column. So if we do that, what we get is this. So the first column multiplied by -2, we get, for this one, we get -2. So this is added to the fourth column. So -2 plus 2 is 0. That's what we get. And for all other elements in the first column, they are 0. So the corresponding elements in the fourth column are unchanged. And next, we apply this matrix. This is P15 of -2. That is, adding the first column multiplied by -1 and add that to the fifth column. So the first column multiplied by -1, we get -1 here, and add that to the fifth column. So -1 plus 1 is 0, and everything else here are 0, so this part is unchanged. And next, we apply this matrix, P24 of -3. That is, we multiply the second column by -3 and add that to the fourth column. So the second column is this. If we multiply this by -3, we have -3 here. So add that to the fourth column. So -3 plus 3 is 0. That's what we get here. And everything else in the second column is 0. So everything else in the fourth column is unchanged. So we have this. And now, next, we apply this. So P25 of -2. So we multiply the second column by -2 and add that to the fifth column. So negative 2 times 1 is negative 2, and add that to this 2, which becomes 0 here, and everything else unchanged. So we have all zeros now. And lastly, we apply P3 4 of negative 1. So we multiply the third column by negative 1 and add that to the fourth column. So that will eliminate this one. So we have 0 here. So in the end, we have 1s here, and everything else is 0. This form of matrix is sometimes called the normal form of the matrix. And any matrix can be transformed into this form by some appropriate choices of elementary operations, row or column. So this is the goal of this video, that is to prove this theorem. Let A be an m by n matrix with R being its rank. Then there are a finite number of elementary matrices Q1, Q2, and so on up to Qs of order m, and a finite number of elementary matrices P1, P2, and so on up to Pt of order n, such that this product becomes this form. So there are ones in the upper left corner of the matrix, and the number of ones here is R. It's the rank of the matrix, and everything else is 0. So if you look at this product, so we apply a series of elementary row operations and a series of elementary column operations. So by an appropriate choice of these elementary operations, either row or column operations, then we obtain this form. That's what this theorem says. Okay, let's try to prove it. From a previous video, we already know that there are a finite number of elementary matrices corresponding to elementary row operations, such that this product becomes the reduced echelon form like this. Here, this is the first pivot column. Let's call it C1, and this is C2, and this is C3, and so on. And finally, we have CR, and R is the rank of the matrix. So we can start from here. That is, we can assume that we already have this reduced echelon form. First, consider this column, that is C1 plus 1. And all the elements in this column are 0 except for the first element and the element in the first row. And we want to make it 0. To do that, we multiply this column by negative A1 C1 plus 1 and add that to the column C1 plus 1. And this can be done by multiplying to this matrix the elementary matrix P C1, C1 plus 1, and negative A1, C1 plus 1. So if we apply this matrix from the right to this one, then this element becomes 0. And we do the same for the next column and the next column and all other columns here. And after applying all these, we get everything in the first row to be 0, except for this one. And next, take the second row and do the similar procedure for all these elements so that they become all 0, and do the same for the third row and up to the rth row. So we can make all these things to be 0. So what we have just done can be summarized in this way. For each I, so I is the row number, 1, 2, up to R, and for this given I, then for each j, ci plus 1, and so on up to n. the last column, multiply this matrix by this elementary matrix, PCij of negative Aij, from the right in turn. Then after all, we have this matrix. So we have ones here, and everything else is 0. So everything here is 0. Everything here is 0, 0, 0. And of course, this was already 0 to begin with. Next, all we need to do is to swap this column with the first column, and swap this column with the second column, and swap this column with the third column, and so on, and swap this column with the rth column somewhere here. Who knows? So this swapping of columns can be done by these elementary matrices. So we apply these elementary matrices from the right again in turn. Then after all, we obtain the desired form of the matrix. And we are done. So that's all for this video. See you later. Bye.
Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.